Our overall objective to have a very practical, functional color system used to help recognize musical patterns, one so detailed that we can actually name the musical patterns and what we're doing with the color system itself. To do that, we need a color system to give us the points that we're working on as well as the distance. The points are typically named in the 12 notes of the musical alphabet or the Nashville number systems, the modal points, and then the distance is usually the intervals. If we have absolute colors for those two things, we can name a movement from one note to another note through simply the color system as we move from a note point or nodal point or modal point to the next place, distance-wise being the interval. To do that, we want to be able to understand what sound is, how we can visualize sound as either like a note number line or a circle, or more specifically, a spiral staircase that has repetition as well as an infinite increase and decrease. And then how color works and how we can map that to have the same shape so that we can give a one-to-one relationship, providing us those absolute colors that we desire so that we can build the association. All right, first, sound has a natural cycle built into it called an octave. So we've discussed this in a prior course or section, in that when we measure sound, it repeats to us in our ear. So that means any culture in the world has got to come up with some system that has that repetition. Otherwise, men and women would not be able to basically sing together because our voices are typically at least an octave different. So that means whatever system we come up with has to have that quality to it, which we can visualize as, in essence, a circle. So for example, the typical example being in the middle of, say, a piano, we're not looking at C, we're looking at the A. The start of the alphabet is measured at 440 hertz. That's going to be the measure of the wavelengths, right? And that goes up to 880, would be an octave up. It would be another A, an octave up. You can see it as a note number line because it's going to be higher, but it also has that quality of kind of a repetitive motion. So we can think of pitch as a note. It's going to be a number line. So in other words, when we start to visualize what is happening with music, we could think of it as a number line going infinitely up or to the right, infinitely back, or to the left, and it does function that way. However, because of that octave quality, we can also think of it kind of like a circle going around a lap. Now this is more of an oval, but a circle, the fact that it repeats is what we're getting at here, meaning that although it still goes infinitely up and infinitely back, it still has a quality of repetition that we want to take into consideration. Therefore, the actual shape that we would like to be able to visualize is more like a spiral staircase. Why? Because a spiral staircase, you can still see the repetition. You can say one right above the other. Those could be like two A's, but one's going to be an octave higher, meaning you still have distance. Now, we can't really visualize a spiral staircase when we're trying to work on something. We can kind of see it. Oh, I get it. It's a spiral staircase. But if I'm trying to work and say, how far away is this note to that note? I'm either going to be thinking in terms of a note number line or like a clock that's going to be basically repetitive, always knowing in the back of my mind that there's actually both of those qualities that are happening. Now, color is a little bit different, although similar. Color, in contrast, is a continuous spectrum of light wavelength. So this is basically all of light, right? And our eyes can pick up some component of the light wavelengths. So this is the visible light that we're going to basically be working with. So obviously we want to take that visible light and then break it out so that we can get a very systematic color system that we can apply to our 12 note system. So obviously this is the range of light that we have to be working in then. Now, when we think about light, they measure it similar in that we actually have a measurement, an actual unit of measure that creates, in essence, the light. And it's usually going to go from the shorter length of light to the longer length of light. So, and that usually goes from this like purple color on the shorter lengths up to this red color to the longer length. So this is the actual spectrum of light that we have. Now notice as the wavelengths get longer, it's not like you get this repetitive quality. It doesn't go back to purple up here or like a darker purple or something like that, which is what happens with pitch. With pitch, as we saw, a 440 wavelengths, if I keep on measuring the wavelengths and they go up and they double to 880, then we have that octave. That's where you get the spiral staircase. It's not here with color. We don't have that. It's not there. Not only that, but you can imagine if I try to bend this into a circle, what's going to happen is the red is going to be at like 11 o'clock, and then it's going to blend into this purple over here. And that's a harsh blend, right? That doesn't look quite right. It doesn't seem like it's going back on itself. We don't have that circular quality that we have in music. But painters and whatnot will want to do that. They're going to want to add that quality in. And oftentimes they actually flip this around. So they'll flip it around this way and have the longer wavelengths first, which is red, and then move down to the shorter. Why would that make sense? Possibly because in our realm of being as human beings, and the light is kind of similar to temperature, I think of it in some ways. And we live in a temperature area where the red is more of a warm color, and then when you go this way, it gets kind of like cooler. Even though if you're talking about like fire for heat, the blue is actually hotter, right? But in our normal everyday human experience, I think it's like warm is red, warm is like hot red, and then it's getting cooler as you go this way. Even though again, if you talked about a flame, then it might be right. So we have this problem of when I try to map the color wheel onto the pitch wheel, one, that it's a spectrum, two, even if I can bend it into a circle, it doesn't fit right. There's a gap between the red and the purple over here. And three, artists like to flip it around so that the red is first. So when they make a color wheel, they typically start with red. All right, keeping that in mind, there's no natural repetition. However, so measuring sound. So how do we measure sound? We've talked a bit about this in a prior course or section, so won't put a lot of time on it, but pitch is measured in hertz, vibrations per second. So basically we can actually measure the vibrations, how many vibrations are happening per second. And then as we measure more vibrations, you can imagine in theory, like a note number line, a vibrations number line, it goes up infinitely and back infinitely. So we can measure it thusly. So color is measured in nanometers, So the length of light waves. So both of them have the quality of measurement. They have different things that we're measuring them by, of course. The number of oscillations for sound or compression waves, however you want to think of it. And for light, the length of the waves. So they're both phenomenons that are similar in that way. We can scientifically measure them. They both result in a spectrum, although the color does not have, once again, this circular quality. Notice what has happened here is we bent it into the circular quality, and this is what we call, in essence, the color wheel that we're going to come up with. So if sound can be put into a circle, then we can also put color into a circle. Now you might say, well, you just put it into a circle. What does that mean? Well, we'll do this mathematically in our projects just to show you how it works, how in essence you derive the 12 notes in the musical alphabet. But in essence, if you think about 440 to 880, that's the distance of the octave. And then what I'd like to do is convert that distance into equal measurements of 360. And you can use like a formula to do that. It's kind of a log idea in order to do that, in order to convert it into a circle. And the reason I want to get it into a 360 degrees, you could just get 12 points that are around the circle, but I'd like to map out, and we will do so in our practice problem, 360 degrees. Why? Because if I wanted to get technical and say, well, what if I was playing like an A, but I bent the string up a bit? Then I might not get to like an A sharp. I might be in between somewhere. And so you might want to look that up on the 360 circle, which you can then map out or tie to the color circle. Now, so that's what we'll do. So color, you can do the same thing. It's also a spectrum. So we can basically map it out and say whatever the wavelength, whatever the lengths are from the nanometers, whatever they are, I want to fit it into equal units of 360. Because if I have 360, that maps onto 360 degrees, allowing me to map it onto a circle. So I would like to have, what we're going to do is line these two things up side by side, color, wavelengths mapped in hertz, color mapped in nanometers, but then standardize each of those measurements so that we're looking at equal distances of 360 degrees, therefore being able to map it onto a circle. Once we map it onto a circle, we can basically treat it like a clock. We can choose 12 equally distanced points on the circle, which will give us the equivalent hertz versus the equivalent amount on the color wheel, which would be 30, 60, 90, 120, 150, 180, 210, and so on. So we can, and that's going to be the letters that we basically are going to be applying. So these numbers over here do not represent hertz. They do not represent nanometers. They represent the relative position if I convert these two distances to a 360, an evenly spaced 360 degree distance, right? And then I can map it onto the circle. That might sound a little wonky, but we actually will work that out if you want to look at the detail, but that's the idea. So sound divide octaves into 12 equal spaces, points, notes, and color divide color wheel into 12 equally spaced hues. So then I just name these 12 points. That's in essence how they derive the 12 notes in the musical alphabet.